the current state of the CO map, where it is in its sort of general timeline of observations. But before I really go into all that kind of detail, I want to step back a bit. I want to take a look at the big picture. Here it is. I'm not going to give a full lecture on physical cosmology right now, but just to say, looking at this sort of timeline and coming all the way from the CMB out to the modern sort of dark energy dominated era, we have very good measurements on the two extremes of that timeline. The CMB has been a treasure trove of verification of the standard model of cosmology, experiments like WMAP, Planck, ACT, SPT, all these ground-based, balloon-based, space-based experiments. I think I'm showing the Planck all-sky map here. And then on the other end of that timeline, the modern day universe, we have surveys like Sloan, the pie diagram from Sloan is shown here. And in more recent times, things like BOSS and DES, DESI and LSST to come, of course. So there's already a significant treasure trove, and there will be even more of a treasure trove of data about the current conditions of the universe. It's this middle bit here that I really want to talk about for a bit, right? Because there is a lot going on here. And we don't necessarily have great measurements across very large cosmic volumes, certainly not on the scale of something like the CMB or something like the ES or Sloan. And there are significant cosmic processes going on here, things like reionization, right? CMB measurements, deep rest frame UV measurements, these have tied down the story for cosmic reionization somewhat, but we still don't have the timeline completely pinned down. We don't quite know exactly when it started and when it ended. And then there are still open questions about what sources are really driving the whole process. I'm showing here on the right panel, right, the measurements as of a few years ago of the rest frame UV luminosity function. The left end is the bright end where everything is quite well determined. And then the right hand end is sort of the faint end, where we don't really quite know, where the luminosity function cuts off, what the behavior of the slope at that faint end is. So we don't know if there are enough faint sources to drive reonizations with sort of what we would typically expect for escape fractions, or if we really need massive sources with very high escape fractions to drive the process. And then moving on a bit further down the timeline, you have the epoch of star formation, galaxy assembly. And there's the history of star formation activity has not completely been down in terms of how much there was in the past and sort of when it peaked. That partially comes down to not having necessarily the best rest frame infrared data at higher redshift. Of course, new starlight is rest frame UV, but a lot of that can get reprocessed by dust, re-emitted in the IR. And so if your empirical corrections at low redshift for that obscuration don't necessarily hold up at high redshift, you don't have a great idea of how much star formation you might be missing out on measuring by just relying on the UV data. You can try and get around that looking at CIB anisotropies. The infrared background has a significant contribution from unresolved galaxies. However, because it's a broadband measurement and there's not really true line of sight information, there are significant degeneracies in trying to model, the contributions from different redshifts. You can try and get around that with cross-correlation against external things like lensing, but the errors are still, it's still early days for these kinds of analyses. And the broadband, the 2D nature of the CIB data presents somewhat of a challenge there for it to tie things down by itself. Now, a common theme here between the reionization questions and the star formation galaxy assembly questions is really we want to characterize the contribution to these processes from faint or otherwise unselected for sources. And so the CIB, that's attractive because it's looking at the aggregate infrared emission from both faint and bright galaxies all at once, in a sense. And so you might think, why don't we try to apply that philosophy, but in a way that allows us to have true line of sight information? And so that's sort of the general idea behind line intensity mapping. you're doing a blind statistical survey, not of continuum emission as with the CIV, but of emission in a given spectral line. And so, 21 centimeter, the idea has been around for decades. And recently, we've started developing experiments to do similar things with the kinds of lines that I'm showing here. This was from an Astro 2010 white paper, throwback. You can see, some of these different lines, all of these are associated with star formation in some way or another. The C2 line up at the top there, sitting near the peak, that's, associated with PDRs. And then, the CO rotational lines, that come in this ladder, those are associated with the cold molecular gas that's fueling the star formation activity. And just in very broad sort of signposty terms. And so, you think about having a three-dimensional data cube, and you think about the way all of these are going to aggregate, you're going to be able to trace fluctuations in something like CO1 to 0 line intensity, and you're going to be able to trace the clustering signature of galaxies associated with that line emission at that redshift. Maybe it helps if I try to show, like a very basic illustration of the idea here. Right, so this is from the Lineintensity mapping white paper from back in 2017. I think Patrick, while he was still at Hopkins before he joined CITA, I think he drew this up and I've just annotated it a bit. In terms of thinking about how Lineintensity mapping compares with something like just a sort of a blind scan for individual line sources, you can think about trying to run surveys with something like the VLA. People do this, but only over hundreds of square arc minutes. If you try to expand that kind of sort of molecular line scan idea to multiple square degrees, that becomes much more of a challenge. After spending thousands of hours on a computing instrument like the Very Large Array, you're only going to really be taking a look at these sort of red dots here, and you're missing out on all of the gray dots that are also potentially CO emitters in this simulation. Meanwhile, with Lineintensity mapping, we're not trying to track down each individual gray dot. You're really trying to measure the aggregate CO flux on the right-hand side there. This is convolved with a 5-minute beam. It's a bit of a coarser picture, but it's fine because you can still basically make out sort of the large-scale, clustering signature of the CO line emission associated with the underlying galaxies. And you'll notice not only do we trace the CO flux from the brightest galaxies, the red dots, but you also can potentially trace filaments or structures associated with the fainter CO emitters, as long as you integrate down deep enough. Just saying as long as you integrate down deep enough might sound a bit facetious, but when you're talking about a 5-minute beam and this kind of observation, in principle, will just require a single 10-meter dish and a decent receiver. That's integrating down deep enough on something like that is certainly a much more realistic proposition than trying to propose for thousands of hours on a community instrument with lots of priorities to balance. So that's the basic idea. And it's gained a lot of traction, especially recently, even outside of 21 centimeter, because of sort of the niche that something like CO or C2 line intensity mapping could potentially occupy in between these wide spectroscopic surveys like DESI, which are only going to go out to so high redshift, and something like a James Webb survey, which is going to go to very high redshifts indeed. It's going to be a very deep survey. It's going to tell us a lot about some of these pre-reionization sources, but it's over fairly small co-moving volumes. Certainly, per redshift interval, it's not a lot of co-moving area you're probing. So, that's why we're seeing a lot of line intensity mapping experiments pop up recently across a variety of lines here. 21 centimeter, obviously, I think that's probably going to be the most well-known around here, Chime, sort of led by our neighbors at Dunlap. And then the C2 CO niche in the middle here, of which we have CO map, we also have CITA prime and time, which we have associations with. And then on the right-hand side, you have sort of the optical line niche, which is a bit more challenging to do from the ground at high redshift. So a lot of these experiments listed are things like ambitious concept studies like CDIM or Origins. You also have SPIRX, which is a mid-scale satellite that is funded and will do spectroscopic sort of line intensity surveys in some of these lines, in addition to some of the broadband studies that they're doing. And it's important to emphasize all of these lines are scientifically important. The 21 centimeter is going to be directly probing the neutral IgM at early times. The C2 and CO is tracing sort of the gas content. And then all these optical lines are more directly tracing star formation with less interaction around it. In terms of the ease with which you might expect a detection in each of these sort of niches, I want to be a bit cautious, about comparing the niches. I will say, the 20 centimeter has, one of the more direct relevances to reionization. There's certainly going to be, neutral hydrogen at reionization. So, it doesn't take much convincing to show that there is a signal. It's just a matter of how sensitive we can be in measuring it. The main challenge there really is going to be the, RFI, the, high foregrounds from synchrotron and free. There's lots of work in these areas, so I'm not going to say these are insurmountable challenges. With the optical niche, as I said, there's poor atmospheric opacity, which means you often have to go to space, which does limit, the agility with which you can sort of move forward in terms of technological developments, incorporating those into your experiments. And it does limit things like potential, even though these are, short wavelength lines, so it's easy to get optical high spatial resolution with a relatively small dish. There's going to be challenges in getting, very high resolution spectrometers, which you might need given how crowded the optical line space is to try and deconfuse some of these lines from each other. So I think CO and C2 also happens to sit in this sort of nice niche in between these two, the 20 centimeter folks and the optical folks, where you have low enough opacity to observe from the ground. So there's some agility there technologically. And then the continuum foregrounds, we kind of sit in this valley between the synchrotron and the dust. So I think it's a nice niche to work on in that sense. And that's the kind of niche where we find the CO Map experiment alongside some of these other experiments, some of which are looking at C2, some of which are also looking at CO, but in different regimes that I'll briefly touch on later. So by now, I hope it's clear that with CO Map, what we want to do is line intensity mapping with the carbon monoxide line emission. We think it's going to be a common bright tracer of star formation activity. It certainly seems to be locally where we see good correlation with the far infrared luminosity, which is to say obscured star formation. And so we hope that looking towards epoch reionization, that broadly still holds. And then line intensity mapping, as I discussed, we're really interested in sort of the aggregate statistics of these galaxies rather than the individual galaxies themselves. Now, it would be nice to say we're just going to build an experiment to start with to just immediately go after the epoch reionization CO signal. But there are a lot of uncertainties around this signal at high redshift. We don't know how dusty, the early universe is, so we don't know how well shielded the CO is going to be. We don't know, we have incomplete knowledge about other processes like CMB heating and so forth, dust temperature and so forth. And so it seems more reasonable maybe to not immediately ask to be funded for thousands of detectors across multiple antennas. Rather, we should start with a Pathfinder that goes after a sort of proof of concept signal that shows that this is a feasible technique to apply potentially even to reionization era redshifts. So that's where this Pathfinder comes in, right? We do eventually want to go after reionization, but we're going to sort of first prove that CO intensity mapping can actually do valuable science. What I'm showing here, right, is the observing band for our initial CO map instrument on this plot of observing frequencies for each of the rungs of the CO line ladder. And you can see, this 26 to 34 gigahertz range that CO map observes in, that's technically got CO 2 to 1 at redshift 7-ish in the mix, but the signal that's really going to dominate is the CO 1 to 0 at redshift 3-ish. And so that's a signal that is interesting in and of itself. It's sort of near the peak of cosmic star formation, but we can also use measurements of that signal to demonstrate that CO mapping is feasible and has potential to look towards deep organization. And we'll be developing technology and techniques that will have utility towards that ultimate goal. And then as a bonus, the signal is still buried in there, the CO2-1, the Redshift 7 signal. So who knows, maybe some analyses, some correlations with external observations or future observations will help us tease that out as well. So, this is sort of the collaboration we have got together here in better times. Here is in front of the actual instrument at the Owens Valley Radio Observatory, the old Karma site. This is a very incomplete list, and I'm sorry, I'm probably leaving out quite a few folks. But Caltech is basically where RPI is, Kieran Cleary, and Caltech's operating the site, much of the infrastructure. And then we have all these groups, Oslo, CITA, Manchester, all these other folks working on various aspects of the modeling, of the analysis, of the pipeline, and so forth. Just to show some instrument pictures a bit more close up, the receiver, is pictured here in its shroud on the top left panel there. Here, below that, you can see, what the receiver looks like before it's put in the shroud under the window, all the 19 feed horns. And then on the right-hand side, just for laughs, here's the picture of the digital back end. That's basically where the actual sort of integration happens. It is a very warm box, but I'm sure it is nothing compared to the sort of GPU clusters that power things like Chime. Just going to flash some specifications up here. The sort of latent antenna the design is very old, but the antenna itself, I think, comes from, was operating before CMAP, was operating as recently as Karma before it was decommissioned. We have some alterations to the optics. The receiver is completely new. It's not a Karma receiver. It's a new receiver with these low noise amplifiers that JPL developed. I'm not going to go into great detail on the specs, but this is just to show you, the instrument exists. It has specifications that seem quite sensible to try and approach a measurement of this sort of difficulty with appropriate requirements on system temperature, resolution, things like that. And so what we're trying to observe is the CO fluctuations, the CO line fluctuations at Redshift 3. And mostly the way we sort of encapsulate that as an observable is as the CO power spectrum, the power spectrum of the CO temperature field at this redshift. Here's a sort of model P of K for illustration, right? You have the clustering component that dominates at low K at the larger scales. And then that, that's tracing the, overall mean CO intensity and sort of the bias with which the CO is tracing the underlying galaxies, or rather the underlying dark matter structure. And then at the higher K end, you have shot noise, which is really coming from the shape of the luminosity function, especially the bright end, how quickly it cuts off, these kinds of details. So it's really looking at the stochasticity of the CO in some respects as well. So CO map, again, it's a relatively coarse beam. It's looking at square degree scale fields. It's really probing something in the lower half of this plot. Some of the other surveys I flashed up in that diagram, that Webby diagram from the 2020 Astro 2020 white paper, like HOPS or AIM-CO, those are looking at higher K, somewhere around 1 inverse megaparsec. And so these are complementary surveys, but CO map, to my knowledge, is actually the only one trying to track down the clustering signal for CO at this redshift in this regime. What can we learn when we have a sensible measurement from CO map? Well, the main thing we want to track down, is extragalactic astrophysics. That's our sort of primary science focus. We think we can constrain the CO luminosity function pretty well. This forecast is getting a bit out of date. We're working on updated forecasts for the luminosity function. But basically, right, the idea is that the clustering component of the power spectrum is tracing the large scale structure. And so we can basically infer some kind of galaxy halo connection. We can back infer the abundances of the CO sources for each sort of given luminosity. And we can even translate these kinds of luminosity function constraints into constraints on things like molecular gas density, or in an alternate sort of formalism, we can think of getting an integrated constraint on the star formation rate density. So that we think is going to be the main test in terms of how well CMAP does in terms of its science goals. There are some speculative alternate secondary science, other science goals. There was a paper by Jose Luis Bernal out that Patrick, before he left CITA, co-authored, looking at potentially doing BAO measurements with CO intensity mapping or intensity mapping in other lines more generally. You can see that their forecast for initial CO map BAO measurements is not necessarily terribly competitive with something like DESI, but it is also worth noting it doesn't seem to be a one-sided limit. It seems like we can actually make some kind of finite measurement with CO map, which would be interesting and would potentially set the stage for for this to be more of a focus for future CO intensity mapping experiments, potentially even going after redshift 4 to 6, where some of the more traditional surveys may have trouble, but maybe we could design a sensible CO survey to go after BAO at those redshifts.
What is IMS3?
So IMS3 is this hypothetical concept for a really far future CO intensity mapping experiment that these guys have just come up for the purposes of this paper, as far as I'm aware. It will be like stage 3, intensity mapping with CO. So yeah, that's, it's very speculative. We of course, don't want to rush to say that, CMAP will definitely do this. But it is, it is something we are thinking about now. And so in terms of maximizing, how much science we can do with it, even within sort of the framework of, trying to think just about extragalactic astrophysics, there are lots of things we can do, things like internal cross correlations between something like 12 CO and 13 CO, 1-point statistics, so the voxel intensity distribution, physically motivated modeling, simultaneous modeling with other lines to try and infer things about the interstellar medium. These are all papers that some of our collaborators have worked on in some capacity or another. For my part, I'm going to focus on some of the stuff I've done in the past, looking at things like interlopers, cross correlations, touch very briefly on line-of-sight anisotropies because I don't think I'll have time to really go into that in great depth. But yes, so lots of different tasks to be done. I'm just going to focus on a few of them that I think I've reasonably tackled. So, it would be nice if we pointed our receiver at the sky and just saw white noise and the CO signal. But of course, there are contaminants. There are lots of them. With a year's worth of wall time under our belt at this point, we think we have a pretty good idea of how to remove much of this. The systematics, the ground-based systematics, and reflections, we think are pretty well controlled. So then it's a matter of filtering out things like continuum foregrounds, which are going to be fairly benign because of the spectral structure, right? CO is tracing large-scale structure. The continuum is just sort of a flat power law or a gray body or a black body or what have you. So they're very distinct spectrally, and so that should make separating out foregrounds like that much easier. One thing, though, one example of a foreground that might be a lot less easy to subtract would be other molecular lines coming from lower redshift that occupy the same sort of frequency space. To show you, what I'm talking about, let me flash back to that sort of centimeter millimeter wave SED, right? Where I was showing the C2 line, the ladder of CO lines. And so remember, we're looking for CO1 to 0 fluctuations. And sitting a bit below CO1 to 0 in rest frequency is hydrogen cyanide. So the HCN molecule has its own sort of ladder of rotational lines. CO1 to 0 has a rest frequency of 115 gigahertz. HCN1 to 0 has a rest frequency of 88 gigahertz. So what that means is if you're trying to look at CO1 to 0 at redshift 3 or so, technically you're also going to have HCN emission from redshift 2 or so mixed in. Now, the bright, you might say, well, looking at this SED, right, even though it's an example, it seems to me that the HCN is an order of magnitude dimmer than the CO1 to 0. That's true. The excitation conditions are very different. HCN is really tracing denser gas than the CO. But depending on how you model HCN, the fact that the mean intensity is much lower than for CO1 to 0 doesn't necessarily mean that the power spectrum is going to be much lower than the CO power spectrum. And so Patrick, before he came to CITA, devised these 2D simulations of CO and HCN line intensity maps based on log normal fields. And what he found was that even though in that model, the HCN mean intensity was, 1/20th of the CO mean intensity, the power spectra actually ended up being comparable, especially towards higher L, so to speak, because these are 2D maps, and so it actually impacts us very, very badly in scales that are relevant to CO map. So that's, interesting. And then the other interesting thing about this is how flat the HCN power spectrum seems to look. That and the fact that, the extreme HCN intensities are very, very high in this model does suggest that, what's happening is there's this, in these simulations, there's this population of very bright, but very sparse, almost randomly distributed emitters that are resulting in this very high shot noise power spectrum for HCN. And so what I decided to do was try to, replicate these models in 3 dimensions, so using dark matter simulations and light cones, but also examining some of the assumptions going behind the modeling of the HCN as well as the CO in these models. And so it's good to review, how exactly, line emission gets modeled in a lot of these cases, whether it's an analytic halo model or whether it's painting luminosities onto dark matter halos. You're making some kind of assumption about the galaxy halo connection when you're converting halo properties into things like line luminosities. And so I'm not going to go into great detail on what each of those, steps that I've listed there involves. Just to say, literature in the past has often assumed that this is a single power law, unbroken power law that's increasing with mass without limit. So you can see here, Tony Lee, who was with us at Stanford, had drawn up this plot of some comparisons with his model versus some of the previous models in the literature, which are all unbroken power laws, whereas Tony's model here has this fall off in plateau in CO luminosity with high halo mass. And we think that's actually the more reasonable thing to do because of the fall off in star formation efficiency we expect at high halo mass. There are feedback mechanisms that kick in with supernovae, with AGN. It's going to temper star formation activity, and it's probably going to be doing that and in the process also disrupting CO gas or HCN gas. The molecular gas is also going to be disrupted along with the star formation activity. So it's reasonable to, it's well motivated to model this turnoff at high mass. And so what we found was that, Patrick's models obviously were also using unbroken power laws for both CO and HCN. And so when we devised the model more similar to Tony's model for HCN, right, where you have Patrick's model is this unbroken power law, Tony's model, the model that I devised that follows Tony's model more has this plateau at high halo mass. It does significantly temper where the HCN power spectrum is forecast to land relative to the CO. With this unbroken power law, your HCN shot noise completely swamps the CO signal in red. But then more motivated, more realistic prescription, we think, that does put a limit on how bright some of these extreme emitters can be, that keeps the HCN well below the CO signal that's forecast. So that was a relief in some cases because we did not necessarily want to deal with mitigation of these kinds of line foregrounds, but it does emphasize the need to be, always re-examining your assumptions about modeling, making sure you have reasonable physical motivation behind it. to some extent at least. Now, so that's, that's one contaminant sort of we can sort of discount for now. But as I showed at the start, there are a whole host of these kinds of potential obstacles to clean detection. And so you might say, isn't there a way to reject all of these systematics and contaminants and be more confident in sort of the CO map data? Be more confident that this is actually observing the CO at these high redshifts that we're targeting. And what I would say is, well, this is where cross-correlation could help us out, right? You can take the CO temperature field from CO map, cross-correlate it against something like a galaxy survey catalog or a different line intensity map. And if there's a positive co-correlation between those two, we can say, okay, well, this CO temperature field really is tracing, the galaxies at this redshift as shown, as cataloged by this survey. So it improves confidence in a detection that might otherwise be merely tentative. But apart from validation, there's a real, valid science case we made for any kind of cross-correlation, because it's going to be much more than just the sum of two autocorrelations. You're going to get synergistic science out of a cross-correlation that you could not get with the two data sets in isolation. And so that's, those kinds of synergies are going to be important when we try to understand the high redshift universe, all these sort of very complex cosmic processes that are at work. So then the question, right, is if we agree that cross-correlation is a very valuable thing for CO map, what do we cross-correlate against, right? What's going to be available at the end of the 2-year observing campaign, which is going to be next year? What's going to be available to cross-correlate against? And so there are two examples I'll discuss here very briefly, one of which is HEDDEX. This is probably something you've heard about because it's been a long time coming. It's a blind search for lambda alpha emitters over a few hundred square degrees. The redshift range is a very good match against CO map. It is a spectroscopic survey, so there's real line of sight information to cross-correlate against. There are some concerns, however, from the selection and the sampling, in terms of do we have enough sources in a CO map observing volume to cross-correlate against? And then, of course, the concern might also be, well, why don't you, well, HEDDEX, it's looking chiefly at the northern sky. It's not going to overlap with certain very attractive fields like cosmos. So ancillary data could be limited in some cases. So that's a real concern. And if you want to chase after ancillary data and something like the cosmos field, you have catalogs like the Cosmos 2015 catalog. This is what is an effectively mass selected catalog. There's a good abundance of redshift 2 and above sources to cross-correlate against across a reasonably sized field. However, the concern is it's a photometric catalog. You don't have true redshift information. You're taking these kinds of pictures, broadband pictures, and guessing at the spectral features. It's very advanced guessing, but it is guessing nonetheless. And so the concern is, how does that affect correlation? How much cross-correlation does that erase? And taking all that into account, we want to simulate these cross-correlations and figure out what is an encouraging target for CO map cross-correlations. So that's what I did. I went and simulated some cross-correlations against various sort of hypothetical galaxy surveys, spectroscopic or photometric. And of course, spectrometers aren't magic. They have, there will be some discrepancies between CO redshifts and optical galaxy redshifts, if only because you expect some level of systemic offsets, between different gas and stellar components in a given galaxy, apart from resolution limits as well. But those kinds of errors aren't going to wipe out your cross spectrum. There's going to be some attenuation at the finest scales, but by and large, the large-scale clustering cross-correlation is going to be well preserved. The effect is going to be a lot more severe once you get to photometric sort of level redshift errors, though, where you are starting to attenuate the cross spectrum significantly across the wave number range where CO map is supposed to be most sensitive. And the level of attenuation combined with sort of the sacrifices in observing efficiency and overhead we'd have to make to overlap with a field like Cosmos from sort of central-ish, southern-ish California, that's enough to make pointing CO map at a field like Cosmos no longer make an overwhelming amount of sense, at least not to just cross-correlate against a photometric catalog. There will of course be ancillary data going forward, but the timeline for any kind of future data on Cosmos is speculative. It's not firm, I think. So then we simulated cross correlations against hepdex. Again, as I said, this is a natural target for cross correlation based on the redshift overlap, based on the survey footprint as well to some extent, which is easier to coordinate than exclusively an equatorial field. We did make some projections assuming hepdex could be used as a Lyman alpha intensity mapper. The survey strategy means in principle that could happen. And that could improve the detectability of cross correlation between CO and Lyman alpha as probed by CO map and hepdex. But you would still obtain a fine detection for CO map cross correlating with Lyman alpha emitters. There is some attenuation, obviously, for a variety of reasons. However, it is not nearly as severe as the attenuation of the signal you get from photometric redshift errors. So just going to flash up the sort of signal and noise as a function of wave number here for some of these different scenarios, including the autocorrelation. This is per patch, I think. When we forecast this, the numbers are plotted per patch, and then you can see the, most advantageous cross-correlation scenarios are, the spectroscopic ones, clearly. But that doesn't include hepdex and cross-correlating with their Lyman alpha emitter catalogs. So that's a collaboration that we're actively exploring at this point. Now, I don't have a lot of time here. Let me just touch on a couple of things very quickly before I end off. This is sort of the last thing I did before I left Stanford. It's sort of speculative medium-term thinking about how we can break certain degeneracies that are present when we deal with just the spherically averaged power spectrum as the main observable. Because we know, the CO signal is not going to be perfectly isotropic. There will be redshift space distortions like any other tracer of large-scale structure that we observe in redshift space. In addition to that, we're not cataloging the locations of individual point sources. We're really looking at a continuous field, and that field is distorted by instrumental resolution, which can have anisotropic response. So not only are you coupling clustering into the quadruple power spectrum, so to speak, via redshift space distortions, but you are also clustering a shot noise component into the quadruple power spectrum in a sense because of your anisotropic instrument response. And so I won't go too much into this, just to say, once we have a very high significance detection from something like CO map, we may want to explore things like this and additional statistics like these to try and break the degeneracies that would otherwise be present in more rudimentary analyses. So, the question then is, how far off is that kind of confident detection? Well, so when Tony Lee wrote his paper, 4 or 5 years ago, he made these forecasts for a Pathfinder experiment, which is where we are now in the project. It was fairly optimistic. We thought we would get something like a 7-8 sigma detection of the fiducial model. But a lot has changed in the past 4 to 5 years. Various parameters have shifted around for pragmatic reasons. We actually have I'm not going to say we have a lot more data on high redshift CO, but we do have more data on high redshift CO. You have data sets like ColdZ, which is Dominic Riker's survey on the VLA. You have more up-to-date empirical modeling of the galaxy halo connection from folks like Peter Baruzzi. You can combine those kinds of new models and constraints to yield better informed models than Tony's model. And then we have about a year's observations behind this. The instrument was commissioned last summer. And so we know a lot more about how the instrument is performing, what kinds of systematics are there, how we can clean them, what kinds of signal loss we see in the pipeline through various filtering and rejection stages. And so we are in the process of better characterizing our sensitivity based on what our actual data look like and what our actual uncertainties look like based on those data. We think we have pretty clean white noise maps, but I don't have anything ready to show right now in terms of any kinds of firm results. Discussions are still ongoing, but we definitely have a much better idea of the sensitivity that CO Map should be capable of at the end of 2 years. Hopefully at the end of 5 years, because we will be proposing for an extended observing campaign. And as I said, we have a better idea of, we think we have a better idea of what the CO signal looks like. Just going to quickly show, the Tony's model here, right, is in the blue here. I'm pointing at it with the arrow, and you can see, you can compare that to something like the UM plus cold Z model that I'm plotting here, which is going to be our new fiducial model, I think. And you can see that the clustering component is de-emphasized in our new fiducial model relative to Tony's old model. The shot noise is more emphasized. That's just a result of improved having any measurements at all of the CO luminosity function from the cold Z survey, where we think there may be more of a bright end to the luminosity function than we thought. Maybe not as much evidence for steep faint end slope as we might have thought previously. So this is, there are revisions to the model that make us think maybe there's not quite as much signal to go after, but it's not an order of magnitude difference, right? It's a factor of order unity here, and all of these are consistent with current state-of-the-art observations, both in molecular line scans and some of the Lineintensity map observations I've shown here. Unfortunately, I won't have time to go into those in great detail, but of course I can chat after the talk. So, very briefly touching on what the project looks like once we have a detection at redshift 3, we will need to build receivers to go after different frequency ranges. There will be some analyses possible with just the 30 gigahertz data, but it's not going to be as good as actually going after CO1 to 0 at redshift 6 to 8 and cross-correlating that 15 gigahertz data with the existing 30 gigahertz data to try and pull out the CO measurement at those redshifts. I speculated before, you might think about going after BEO redshift 4 to 6. That will also require custom receivers. So either, whatever your sort of science goals would be with future CO map experiment or an IMS3, you're going to need to build new hardware. That's going to require new antenna designs as well, obviously. But even setting aside the hardware challenges, I think we will need improved modeling of the CO signal at high redshift. It's going to be necessary to have physically motivated models to really disentangle signal from interloper, and as well as interpret the signal properly, put it in a proper physical context that makes sense alongside all these other observables, alongside more conventional galaxy surveys and their results. So that's where I'll wrap. I think Lineintensity mapping fills a very interesting niche by looking at the aggregate contribution from both faint and bright sources. CO map is going to be part of that story. We're going to try and map CO fluctuations at redshift 3 to constrain molecular gas content at that redshift. And we're going to try to maximize science output through cross correlations externally, and looking at other statistics related to the power spectrum, and of course continuing to update our models. There's a lot of theory work that needs to accompany any future developments on the experimental side. So that's it. Thanks for your time.
Great, thank you so much for a great talk. Let's all give Dongwoo a round of applause through the reactions button if everyone has that. And then we can move on to questions. We have about 8 minutes. I can see that Wei Li has his hand up. Would you like to go first?
Hey, yes, obviously, thanks for the updates. That's good to hear. I know every time I hear the talk on the CO thing, which is obviously the fascinating window, I always push to ask if anyone has tried using existing arrays like the GBT ammonia array to at least measure that signal. Do you know what that status is? You know, because with existing instrumentation, one can go a long ways.
I haven't heard anything about the GBT array. What I will mention is going back to this diagram here. You have experiments like COPS and MIME, where Cardo Keating over at I think CFA now has played a significant role in each of these. Cardo's, I think, the PI on MIME, and these are basically sort of impatient experimentalists' intensity mapping designs, where COPS was using the SZA to go after the CO 1 to 0 shot noise at redshift 3. There was some legacy data archival data that they analyzed, and then some targeted observations that they made. That resulted in a tentative detection, like 2-3 signal level. MIME is another initiative that's kind of a spiritual successor almost. It's looking at CO, all kinds of different CO lines through things like ALMA and SMA, and I think VLA as well eventually. I know SMA observations have been made for those. They recently published some results from their ALMA observations, both looking at aspects data and looking at their own MIME-specific data. And so that's really looking at CO3 too at redshift 2, 3-ish. They have some very fixed assumptions about how they decompose that shot noise measurement, because that shot noise measurement has a lot of different CO transitions mixed in. But yeah, broadly speaking, I don't know that GBT, it's a pretty big dish. I don't know that the field of view would be large enough for something like this to be interesting for.
Well, but the thing is, because it's a single dish, you don't care about the field of view, because you get the 0 mode. What you do is you scan, mosaic any size of sky you want, and you get all K ranges, which is why it has so much more sensitivity, because it exactly catches the intensity signal and not just the individual objects. With ALMA, of course, you only see the individual very, very brightest object, and the faint random ones get resolved out, and you see nothing from them, and there's no collective large-scale structure. So with the GBT, because it's so much more sensitive and goes to much higher K and has cryogenic receivers, and it's got so many, well, it's got 7 pixels, but still, just given its size, it far compensates for its for the telescope time you might need. That my estimate has always been it's very, very promising if somebody just sat down and took some data.
Yeah, unfortunately, I'm not aware of anyone that's done it. A lot of effort towards doing very pilot surveys for shot noise with ACA and sort of compact configurations of some of these community instruments, but not, to my knowledge, something like GBT.
Okay, good. I'd love to follow up. Maybe we can talk sometime about what one could learn there.
Yeah, I think we should.
Okay, did anyone else have questions?
Could you say a bit more about what types of intensity mapping are best going to constrain reionization?
So, as I think I said, the H1, right, that signal is going to be there because there's just neutral hydrogen everywhere. That's all there is before reionization happens. Yeah. So that is a signal that is assured, and that is a signal that will directly probe the topology of reionization. I think the challenge with CO and C2 is trying to figure out if those, partly it is going to be a challenge of trying to figure out if those signals do exist to be probed at reionization. CO especially, because if the environments are not sufficiently favorable, all the CO is going to be dissociated at high redshift. C2 maybe has a better chance. I think we think it has a better chance of being observable. And if C2 is observable, that would be more or less probing the sort of distribution of ionizing sources. So it's complementary. It is just somewhat more speculative than 21 centimeter range. H alpha, alignment alpha, these sort of very high, very, very high frequency, optical lines, spherics is targeting them at high redshift, but not, you know, H alpha only up to around redshift 4 or 5, Lamma alpha to higher redshift, but I'm not sure how confident those measurements are going to be, especially during the reionization epoch. So I don't have a good answer for you on the optical end. But I think I've told you what I think is the state of things on the lower frequency ends.
I had one question, and perhaps you already touched upon this, but I remember you talking about the HCN interloper line, but you were also showing a couple times the fact that there's 2 different CO lines that appear, and you kind of focus just on one of them in a certain redshift range. How do you differentiate between the 2 of them?
So you're talking about basically a scenario like this, right? Where you do have CO, you know, in our 30 gigahertz band, we have CO1 to 0 at redshift 3-ish. You have CO2 to 1 at redshift 7-ish. You technically have CO3 2 at redshift 10-ish, 11-ish. But the fact is, you know, in terms of how much CO we expect there to be, we don't expect there to be much. You know, we expect it to be most abundant at something like redshift 2 to 3, where the star formation history is peaking, and there's a lot of molecular gas that it has to be there to fuel that. Redshift 7, you know, there's an order of magnitude less star formation going on than at redshift 3. So we expect that signal to be fully subdominant. The thing that we worry about really most of the time when it comes to Lineintensity mapping interlopers is other molecular lines coming from lower redshift, not so much higher redshift. Higher redshift, it's unlikely to be brighter, and it's also further away. Lower redshift, there's a real risk that you're looking at a much more active time for whatever activities lines are tracing, and they're closer to you. So, and when you look at C2 intensity mapping with something like CCAT prime or time, there's a lot of work in the literature and simulations that's been done to try and address the problem of CO transition lines being mixed in with the C2 signal at reionization.
Okay, thank you. All right, so it is 4 p.m. So we're gonna have the Zoom room still open for the next hour for anyone who would like to continue to chat with Dongwoo. But in the meantime, for everyone who's heading out, please let's give him another round of applause, and thanks everyone for joining.